Hello, Dr. Julian, Julian Nollian.
Hello, how's everybody doing today?
I'm doing good. Good, sir. Hello, Dr. Julian.
Hello, Dr. Julian.
Hi.
Good afternoon, everyone. Right. Are we ready to go? Yeah.
Yes. Hello, everyone. A very good afternoon. So we have Dr. Julian Onions again. Welcome back, Dr. Julian Onions.
Thank you.
Nice to have you. Hope you're doing well.
I am.
All right. Okay. So let's get started with the movie review of Interstellar 2014. I believe it will be really interesting. I'm excited as well. So over to you, Dr. Julian Onions. You can start.
Okay. Thank you. Let me just share the screen. There. I hope you can see that.
Yes, it's visible.
Great. Fantastic. So I'm not going to go through the whole film, obviously, because we'll be here for an hour and a half or something as we went through it. So I thought I'd pick out some interesting bits I found from the film and talk about what we know about them and what we don't know about them and how things change. So I'm going to start with the big one, really, which is the black hole itself. So you probably know they travel through space, and we'll get to how they travel through space in a few minutes to visit this very big black hole, and it's called Gargantua. I think that comes from either the Greek or the Latin Gargantua, meaning something very, very big. And this is a very, very big black hole. So what do we know about black holes? We know a certain amount from black holes in our own galaxy, which are much easier to study because they're much closer. So we know how simple black holes form or smaller black holes. So we measure things in terms of weight, in terms of how big they are compared to our sun. So we talk about things in astronomy as solar masses. So one solar mass is the weight of one sun, our sun, basically. So we can say things are one solar mass, it would be the same as our sun, or half a solar mass, it would be half the size, or two solar masses, it'd be twice the size. So most black holes that we know about, or we discovered early on in our own galaxy, weigh somewhere between 10 and 50 solar masses. So they're about 10 times bigger than our sun to 50. Well, actually, that's not true. They can be from about 4 solar masses up to about 50 solar masses, something like that. And these happen when a really, really big star, much bigger than the sun, so it has to be at least 10 times as big as the sun, ends its life. And when that happens, it's been in a balance between burning and the gravity of the star trying to squash it down for so long that finally it gives out and the gravity wins and everything squashes down. And if it's the size of our sun, it just squashes down to a tiny star, which we call a white dwarf, which is not very big. It's about as big as the Earth, but that's a lot smaller than the sun. And if it's a bit bigger, then it squashes down to something else called a neutron star, and that's much smaller. That's about 10 kilometers across, so the size of a really big city. But if it's bigger than that still, and we're not quite sure exactly how big that has to be, but it's somewhere between 4 and 5 times the mass of the sun, so 4 or 5 solar masses, then it ends in a black hole and it just collapses down to nothing. And we really don't understand that bit because most of the physics equations break down at that point, and we just don't really know what happens within a black hole, because nothing can get out of a black hole. You can put stuff in, but it can never come out. So you could send an astronaut in, but he couldn't tell you what would happen because he couldn't, there is just no way he could communicate. He can't send out radio, he can't send out light, he can't send out anything. So that's one of the tricky bits about black holes, is that even though we can see them, but they're not very close. Even so, they are very difficult to get information out of. So that's the regular black holes, and we know how to make those. We've actually simulated those. We understand quite a lot of the equations around those. But things like this gargantua that they go and visit in the Interstellar movie are vast. This weighs 100 million solar masses. So that would need 100 million stars like our sun to get together to form this. And one of the problems in astronomy is we don't know how that happens. So we need somebody clever or somebody with better insight to go and work that out. So that could be one of you. One of you could work out how to make one of these huge black holes. We call them supermassive black holes because they're so big. There's one at the center of the Milky Way, which is much easier to look at because it's a bit closer. It's about 30,000 light years away, something like that. So that's not very close. But we don't know how to make them. And we know they form quite early in the universe. So they need to be made quite quickly. We could probably work out how to make one very slowly over billions of years. But we know they have to be made in a very quick time because we see them very early on in the universe. So that's one of the problems, is how do you make one of these huge supermassive black holes? And nobody's got a good answer to that yet. So if any of you become astronomers, that could be an interesting question to tackle. How do you make a supermassive black hole? Because there seems to be one at the center of every galaxy we've looked at. So they are pretty common. There must be a common way to make them, but we don't know what that is. Now, in this image, you can also see the little planet that they go and visit in the Interstellar movie, and we'll come on to that shortly. So that is orbiting very, very close to the black hole, and it's perfectly safe there. As long as it doesn't get too close, you'll be fine. You can orbit around it. It does have some very strange effects when you get very close to a black hole, but you can orbit around a black hole with no problems, just like you can orbit around the sun without any problems. As long as you don't get too close, you'll be safe. So they're not as terrifying as you might think. They are, you shouldn't go and play with them too crazily, because if you do get too close to them, there is no way to come back. But it's a bit like swimming in a river, and there's a waterfall a bit further down the river. You're fine swimming in the river, but if you get too close to the waterfall, you might get sucked over, and that would be the end of you. So it's a bit like that. You can swim upstream from the waterfall without any problems. Just don't get too close to the waterfall. Now we have seen, we've analysed the black hole at the centre of our Milky Way and looked at how that works and got some information from that. And you may well have seen this picture that was taken of M87. That's a nearby galaxy, and this was a picture taken of this black hole. It took a lot of work to do it. It took a telescope that was about the size of the Earth. It was lots and lots of radio telescopes attached together to actually get this image, because it's a very, very small image by the time you look at how far away it is. Even though this is one of the bigger black holes around, this is about about a billion times the mass of the Sun. So this is even bigger than Gargantua. But it's still very small compared to the size of space. So it's a lot harder to see. In fact, this one's 6.5 billion times the mass of the Sun. So really, really big. So that's a quick introduction to black holes. I wonder if you've got any questions at this point on black holes before we move on to the next subject, which is how we get to Gargantua.
All right, Dr. Julian and Niels, thank you. Any students who have questions, you all can ask. Neva, yes, you may ask a question.
What is the largest black hole?
Well, we don't know because we haven't found them all yet. But,
The largest black hole that we have found.
I think the one in M87 is pretty big. That's 6.5 billion solar masses. I think there is a bigger one somewhere. As you get further away from the Earth, it's harder and harder to work out how big they are because you see less and less information. So they don't come with like a tag saying I'm this heavy. You have to work it out from scientific measurements. And it gets harder and harder to do those measurements as you get further and further away from the Earth. So the ones in our local neighborhood are the ones we studied most carefully, and we've got some idea how big they are, but there could well be lots and lots of bigger ones yet to be found, which we'll find using new telescopes eventually. Good question. Thank you.
Sudhita?
Actually, what is the biggest black hole in the universe?
And that we still don't know yet. When we get better telescopes, there's one we are going to build in space in about 2030 called LISA, which will look at gravitational waves from black holes, and that will be able to study black holes out to a big distance. So we may be able to find much bigger ones. That'll be about ready when you've probably graduated and ready to make use of it. So it might be you who finds which is the biggest black hole in space.
I have another question too.
Yeah.
Actually, I have heard that there is a machine that has making small black holes, and some theories have suggested that it could, if it takes, because when it sucks more things, that means it will get larger and larger. And so some people theorize that it will actually get big enough to suck the whole Earth.
Mm-hmm. That's a good question. So if you make a really small black hole, the thing with really small black holes, which I'm talking about ones that are just a few centimeters across, they don't last very long. They have a way of evaporating, so they last a very, very short time. So as they get bigger and bigger, they last much longer, and they get a lot more time to eat things up. So if we made a big black hole or made a small black hole near the Earth, then it would indeed eat everything that was around it. But after a while, there wouldn't be anything left around it, so it wouldn't have anything else to get bigger with. So it would be a very dangerous thing to make a black hole on Earth. We did look at when the Large Hadron Collider in Switzerland was switched on. A lot of people thought they might be making very tiny black holes in that. But anyway, it turns out they didn't. And even if they did, they would evaporate very, very quickly in seconds. So they wouldn't really get a chance to make anything. So it's only the really, really big ones that last a long time. So those are the ones we've got to make sure we don't make. Got another question there?
Right. Next, we have Arudit. Arudit, you can ask the question.
Well, how can we make a black hole? If we make a small black hole, how can we make one?
How can we make a black hole? That seems very hard. You have to get a lot of stuff, a lot of whatever you want to make it out of, together in a very, very, very tiny space. So we don't really know how to squash things that hard. We can do it. You can do it with gravity, but you need a lot of gravity. So that's why you need something about as big as a star to make a black hole. We don't really know how you'd go about making one on Earth by squashing stuff together. So that's just a question we don't know the answer to at this point. Thank you for that.
Right. Next we got Tisen.
Where is M87 black hole situated?
I don't know exactly. It's about, I think it's about something like 1 million light years away, a few million light years away from us. It's in a galaxy. The galaxy is called M87. Anything that starts with an M number was from the Messier catalogue found by a French astronomer back in about 1700, I think it was. But he found all the nearby ones. So anything with an M in is fairly close to us. It's still a long, 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 long way away, but much closer than anything else that we've studied. Right, if that's all those questions answered, we'll go on to the next bit of it.
Is that all, guys? Any other questions?
Oh, got another one.
Anyone else? Adisha, yes, Adisha.
Dr. Julian onions, yeah. A black hole going to another place in one place?
Is it going? Most of them, when they form, they stay where they were made. It's fairly unusual for them to move around unless they are in a very chaotic environment, somewhere like the very center of the galaxy or something like that. And if they get too close to another black hole, if they both get very close to each other, they will sort of consume each other and make one bigger black hole. So it's just like sort of mixing two things together.
All right. Anyone else, guys? Got any questions? Is that it? Okay. All right. So Dr. Julian.
Right. So the next topic is, how did they get to the place they went to? So they went to this Gargantua black hole, which was in the center of a galaxy far, far away. They don't actually say where it was because it's a story, I guess. But they have to travel there, and there isn't an easy way to travel a long distance. If we wanted to go to the nearest star and we could build a rocket that could go as fast as we could possibly make it, it would still take 4 years to get to the nearest star. To get to the nearest galaxy, the next galaxy, it would take 2 million years, even in the fastest ship we could possibly imagine. So to get to somewhere like Gargantua, which is in a very distant galaxy, you have to take a shortcut, and that's where wormholes come in. So these are something that Albert Einstein and others worked out are possibilities. So it's a bit like drilling a hole through the earth. You could go from, so I'm in the UK, so we could go from the UK to Australia, which is the opposite side of the earth, and we have to go all the way around the earth. But there is a shorter way, which is if you could drill a hole right through the earth, you would go there quicker. And the same sort of thing applies to space, we think, because nobody's actually proved it. So it could be like, I hope you can see that. Oops, clicked on the wrong thing there. So you could go from here all the way around from one place to the other, following the natural way you go with space. But there might be a shortcut, which is this wormhole, which is a connection which you get by deforming space so that it connects to another part of space. And it's a sort of like a very quick shortcut between two places. Now, these are something that has come up in equations of science that they could possibly exist. But at the moment, although we think they are possible, they are extremely difficult to make. And even if you can make them, they take just a phenomenal amount of material to make. But even if you can make them, they don't seem to be very stable. So you could make a connection between one part of space and another part of space, but it seems to collapse on itself very quickly. So it would probably shut before you could go through it. So it would be a very dangerous thing to go through. So people have looked at seeing if you can make these more stable. Could you make them last longer? Could you make a connection between any 2 points in space that you could travel very quickly? And nobody quite knows the answer to that one either. But it's a very good technique in movies and things for getting somewhere very quickly. You just travel through a wormhole. And there is some science behind them, but at the moment, they are not a practical thing. You can't actually make these things because they just require huge amounts of resources. You would need many, many stars brought together in the very same place to actually make one of these things. And then it wouldn't last very long. So until we get a better understanding of these, they're a sort of a clever way of jumping from one place to another, but we don't really know how to make them, and we don't know how to make them strong enough. So it's not like making a road that you can put down and it will last there for many years. These things, if you could make them, perhaps only last for a fraction of a second. So they're a clever idea, and we might be able to do better in the future when we understand them more. And so on. We've never made one. We've only written about them on paper by using mathematics. So that's as far as we've got with these things. But they are something that might turn out to be real, and it will need somebody clever to go and find a way to exploit those. So that's how they travel. There are other ways of traveling through space. So you can certainly use rockets, but I've said they're very, very slow. Another possibility is something that comes from Star Trek originally, the warp drive. I don't know if any of you have seen Star Trek or any of the films, but they travel through space using a warp drive. And that is a practical thing. There are people who've worked out the equations for making a warp drive. But again, although you can work it out on paper, nobody knows how to make one in practice. So those are a couple of problems that we have from getting from one place to another in a reasonable amount of time. So any questions on traveling through space, either by rockets, warp drives, or wormholes?
We got Sudhita. Sudhita, you may ask a question.
Actually, have we seen or have we found any wormholes?
No, we haven't seen any. We're not extremely sure what they would look like. We imagine they would have some sort of light or X-rays or something associated with them, but they might not be very strong. So they might be a long, long way away and not be very bright. So they might be very difficult to find, even if we went looking for them. Nobody's found one yet. And I say they could be created naturally in certain circumstances, but we think they would collapse very quickly. So you'd have to be very quick to actually catch one.
I have another question.
Mm-hmm.
Actually, now our universe is expanding faster than the speed of light. So can we actually get out of the universe actually by creating a warp drive that is faster than the speed of light?
If we could make a warp drive, yes, we could. We could go to lots of places. If you look at the people who've investigated warp drives, there are a lot of problems with them. So we don't know quite whether we could make them. But if you could make them, you could travel to almost anywhere. You could certainly travel to the next galaxy. You could fly around our own galaxy. And you could probably go to very distant galaxies that are right on the edge of space. But at present, they seem to be very, very difficult to make. They need things that we don't even know how to make to make them, if you see what I mean. They need something called anti-energy or negative matter, which we don't know how to make.
My last question is actually how if we take a normal rocket and we put as lots of fuel as we can, and if we try to go out of the Milky Way galaxy to the Andromeda galaxy, actually, what will it take?
If we could build a rocket much faster than any rocket we could build at the moment and put the fuel on, it would take 2 million years to get to the Andromeda galaxy at the fastest speed we could get a rocket, which is the speed of light. So it would take 2 million years to get there. And that's not, I don't think I'm going to live 2 million years. So I don't think I would get there.
Thank you for that, Dr. Julian Onions. Next, we got Nevan.
Is there any proof that we might find a wormhole one day?
We might do. We do keep looking for them, but we don't really know what we're looking for. That is one of the problems. We've come up with this idea that they might exist, but what would they look like? You know, what sort of what color might it be? Where might it form? So when we're looking for things in astronomy, we do look out for things that we don't understand, and most of those we found the nearby things we don't understand, and quite a lot of them we managed to explain. But we keep looking out for things that are a bit odd, and something that looks a bit odd might well be a wormhole. So we'll keep looking for them, but nobody's found one yet.
There's another one question I have.
Mm-hmm.
What made scientists believe that there are wormholes?
What sort of scientists?
No, the astronauts and all the people research. What made them believe about the wormholes?
Oh, what made them believe about it? They have an interesting history in that I think it was Carl Sagan who was writing a book, and he was a scientist, and he was writing a book about a science fiction book about travel to some distant place, and he wanted a way to get from here to there very quickly. So he went to talk to some theoretical physicists friends he knew and said, I want a way that is realistic to get from here to there in a very, very short time. And they said, well, you can't use rockets because they're just too slow. We don't know about warp drives. They might be possible. But one of the solutions to Einstein's equations says that you could have these connections between bits of space. So, and they called it a wormhole, and that's kind of where it came from. So since that came up, they sort of scratched their head and thought about ways to do this, and this was one of the ways they came up with. It's the mathematics of it say it should be possible, but not everything that you can do in mathematics you can do in real life. So we don't know whether that can come about.
Thank you so much, Dr. Julian.
Thank you for the question.
All right. Next, we got Arudit.
Excuse me, Dr. Julian Onions. I have another question, and it is, can we make a wormhole to another universe if one exists?
Oh, that's a really good question. So can we make a wormhole to another universe? Well, firstly, we don't know if other universes exist. Some people think they do, some people think they don't. So we don't have proof one way or the other. But if they do, wormholes might well be a possible way to get from one universe to another. So that is a very good question, and one we don't know the answer to at this point. Some people think it might be, some people think it won't be. So in science, we always like to have proof. We like to say, well, if you think this is true, show me the proof. Show me how you would work out whether this is true or not. And nobody quite knows how to do that at this point. So there's another question that you could answer when you become a famous scientist. So I look forward to the answer to that. But at the moment, nobody knows.
Thank you, Dr. Julian Onions.
Thank you for the question.
All right. Okay. Anyone else?
No,
Is that
sir.
all? All right. Okay then. All right. Dr. Julian Onions, let's move on to the next phase.
Okay, so the next bit, which is actually my last bit, is about tides and times. So one of the interesting scenes in Interstellar is where they land on this planet, and I'll show you a clip shortly. And they see this huge tide come towards them. This we know about tides on Earth. We see these tides on Earth, mostly caused by the moon and the sun. So when the moon is close by, it raises the water up just a small distance, and that moves around as the Earth spins. So we have a high tide each day. In fact, we have 2 high tides each day and 2 low tides, which is this bulge of water caused by the moon. Now, the moon is not a very heavy body compared to the Earth. It's about 80 times less heavy than the Earth. So it doesn't make a very big tide. And when it's working with the sun, so when they're both pulling together, you get a slightly higher tide. And when they're not working together, you get a slightly lower high tide, if that makes sense. But this planet they land on around Gargantua, this very big black hole, obviously at nearly 1 billion times the mass of the sun, it will make a very, very big tide because it's very close. So they see this very, very big tide, and I hope this works. I'll show you this. So that's the sort of tides they see there, which is caused because they are quite close to this black hole, which has a very extreme gravity. So it doesn't just raise the water by a few meters every day, which is quite gentle. It raises it by hundreds of meters as it comes around. So they didn't really realize that when they landed, and then this huge tide bulge came around, and they all had to get back in the spaceship very quickly and leave. So that is one of the strange things that can happen with these things. And the tidal forces get even worse as you get close to the black hole. So when you get very close to the black hole, and it's actually worse with a small black hole than a big black hole. A big black hole like Gargantua, the tidal forces, although they're extreme, they're spread out quite well. But if you got close to a smaller black hole, one that weighed maybe the mass of the sun or a couple of times the mass of the sun, then the tidal forces get very, very strong. So what is being pulled nearby, you only have to be like a meter or 2 further away, and you feel a very different force. So if you were sort of upright, the forces on your feet would be much stronger than the forces on your head. So as you get closer and closer, those get more extreme. So your feet start to get pulled towards the black hole much quicker than your head, and it just stretches you out. That would be a rather nasty end to you, I suspect. And that's called spaghettification, where you're dragged out into this very long stretch. Well, not just you, anything that gets close is dragged out because the tides are so strong and so different between your head and your feet. So that is something you have to look out for. But with a really big black hole like Gargantua, it's not quite so extreme. You will get to a point eventually where that is extreme, but by that point you will be probably dead from lots of other causes. So it won't matter quite so much. Now, the other thing that happens is when they land on this planet and they see this huge tidal wave coming around, they are deep within the gravity of Gargantua, so they are affected quite strongly by the gravity. So it's doing several things. Not only is it making this huge tidal wave that comes around the planet and nearly destroys their spacecraft, but deep within gravity, the closer you get to a really strong source of gravity, time begins to slow down. So we know this happens on the Earth. It slows down very, very tiny amount. So if you're on the top floor of a building, you will live very slightly longer than if you're on the bottom floor of the building. But you know, even over a lifetime, it will only be milliseconds that you will live longer on the Earth. But because everything is much more extreme with a big black hole, the time slowdown is much stronger. So when they leave somebody up in space around a bigger spaceship, and they take this small one to land on the planet, and this slows down their time compared to their colleagues on space. So when they return off the planet back up and meet their friend back up in space, several years have passed for that person, and it's only a few hours for them down on Earth, down on this planet. So that's something you have to be aware of, that clocks lower down run much slower than clocks further up. This is really, really difficult to measure, and until we got very precise atomic clocks, we couldn't actually measure this distance. But we've done it many times. We put atomic clocks on airplanes and flown them around and then landed them. And when they land and you put them next to a clock that hasn't been on the airplane, they are running at different speeds. So one has gone a bit slower than the other. And most significantly, we have to take this into account. So if you use a GPS system to navigate in your car, or on foot, or even on a mobile phone, so that is using satellites that are in orbit around the Earth, and their clocks are running slightly quicker because they're not quite as close to the Earth. And if you don't take that into account, if you just say, I don't care about that, over about a day, you would be about 20 kilometers away from where you thought you were. So when they were making these satellites, they had to take that into account. Otherwise, every day you would be 20 kilometers away from where you thought you would be, and then 40 kilometers and 60. So you have to take these things into account. Even though they're very, very tiny effect, they are quite significant. But on something within, say, a huge black hole, then or very close to a black hole, it's even stronger. So time will slow down very, very significantly. That's one of the things that came from Einstein's equations. So he was a very bright chap. Obviously, he made these equations in about 1914, I think it was. So they're over 1917 they were proved. So over 100 years, and nobody's found really any serious errors in them. We know they're not the complete answer to everything, but everything he predicted seems to have come true so far. So does anyone have any questions on either these giant tides? Yes. This is my last bit of the film that I'm going to talk about. So you can ask questions about this or anything.
I have a question. What's black hole gravity's name?
It's just gravity, but it's a very much stronger form of gravity. So we feel sitting on the Earth, you feel 1g. That's one gravity worth. That's what's holding you onto your chair or onto the floor, and that's why you can't jump up. If you go to a smaller body like the Moon, it's about 1/6 of that. So you can jump about 6 times higher on the Moon than you can on the Earth. But when you go to a black hole, it may be thousands of times stronger. So then it's very, very difficult to do anything because you are pulled down by the gravity of the black hole. So it will be very, very strong.
Okay, thank you. Next we got Sujita.
Actually, what will happen if it was very close to Gargantua?
If we got very close, it depends exactly how close. So you could get quite close if you were in orbit. If you were just going around and around it, you could get quite close to it. Once you got too close, you would start to feel this this pull of gravity that was different between each side of you. And then eventually you get to a point called the event horizon. And that is like going over the waterfall in the river. Once you get to that point, there is no possible way to get out of the black hole, no matter what you do. You could have the fastest rocket ship in the world. You could have a laser. You could have a radio. Nothing will get out once you've gone past that point. There wouldn't be a particular, you probably wouldn't notice as you pass that point, except you would no longer be able to get out at that point, and nobody would be able to see anything you did. So that's why you should not get too close to a black hole. Not that it's going to be a problem for most of us. I don't think most of us will ever see a black hole in our lives, at least close by.
All right, thank you. Next, Rakit.
Sir, how can we say that the time run even faster than we are in the ground? Sir, like that picture you showed.
It's not something that comes naturally. When you think about it, it's not something that's obvious. But this is what Einstein's equation said would happen. So when people worked out what the equations meant, they found it should mean that clocks run slower the closer you get to a strong gravitational force. And as I said, it took many, many years to actually prove that, because it doesn't change very much. If you lived all your life on the very top of a mountain, you might live, say, a couple of milliseconds longer than somebody who lived down in the valley. So over 70 years or something like that, you might extend your life by a few milliseconds. But so it's very difficult to measure. So you need very, very precise clocks to actually go about measuring it. So that's why it took a long time to measure. So Einstein suggested it in about 1917, but I don't think it was until about the 1950s or 60s that we could actually work out an experiment to say, yes, he was right, and it does run slightly slower the lower down you get.
All right. Arudit?
Does it take a long time to go and get eaten by a black hole? If the black hole eats us, will it take a lot of years for the black hole to eat us, even though we don't see it?
So if the black hole was eating you, let me think what would happen. So it depends which point of view you are. If it's you that's being eaten, you would just fall into the black hole, and you would probably get faster and faster as you fell through it, but you wouldn't notice anything particularly different until you got very, very close. Then you get this stretching force that pulled you out, but you would probably be dead long before that. So that wouldn't be a problem. If you were another astronaut in a spaceship watching somebody fall in, that looks a bit different, because time slows down for them, as you would see them move slower and slower and slower, and almost come to a stop as they got close to the black hole. in fact, let me just stop sharing so you can see me better. So you would go slower and slower and slower, and people watching you would see you almost come to a stop, and because time would now be moving very, very slowly for those people, according to where you look. So you wouldn't really see them fall into the black hole. They would just slowly disappear and fade away. But for the people who was actually falling into the black hole, they would just go in at a normal speed. So it looks very strange and very different depending on who you are and where you are.
Okay, Dr. Julian. Thank you, Dr. Julian.
Thank you for the question.
Thank you very much for that, Dr. Julian Onions. Is there anyone else who wants to ask a question?
No, sir.
All right, David. Anyone else? No? Okay, then. So that's the end of today's session, the movie review of the Interstellar 2014. So before I let Dr. Julian Onions go, I just want to say that we have the preparatory session for a few kids who will be joining the 4th batch for the astronomy camp. Dr. Julian Onions, will it be possible for you to give a benefits of learning astronomy so that these kids know what they're doing, if you don't mind, if you can spare some time with us?
Yeah, just now. Yeah. So we have a lot of students at the university who learn astronomy. They come to learn physics because that's where you start, and then you go into astronomy if that's something you wish to study. And then some of them, I guess most of them, finish after their degree and they go and get a job somewhere, either in physics or some other area. Because if you have a physics degree, it's reasonably easy to get a job because you have a lot of very good skills. You have some good maths, you have some good problem solving, and employers like having students who've done physics and astronomy. If you want to go further and become an astronomer, the next thing you have to do is take a doctorate, a PhD in astronomy. So there you work for 3 or 4 years studying one tiny aspect of astronomy and making some new discovery with help from people who've done it before. They will suggest what they think might be an interesting area to study and something that you could go and work on. And so some people like to do that. They like to take their studies further and become a doctor like me, I guess, and study that. And then some of those will go on to study even deeper into astronomy and become full-time astronomers eventually. But that's only a small proportion. Quite a lot of people, I would guess, at our institution, we have maybe 15 or 20 PhD students who are working towards their doctorate. So every year, about 10 of those will graduate. And of those 10, maybe 1 or 2 will go on to do more astronomy. And 8 or 9 of them will say, actually, that's enough at this point. I don't want to do any more astronomy. I still like astronomy, but I don't think it's the career for me. And being an astronomer isn't paid particularly well. I mean, it's an okay job and you get paid a certain amount, but you can get paid a lot more for doing other jobs using the skills you've learned being an astronomer. So some of the people I've worked with over the last few years have gone off into various different things. I know one has gone to work for the organization that produces maps for the UK and some of the rest of the world, called the Ordnance Survey. So he isn't drawing maps as such. He is looking at the data that comes in from maps and trying to work out new ways of looking at that data and working out what can be done with it. He initially looked at all the data they had about the UK and just looked for some strangeness. So he found places where the land was at a certain height and then suddenly dropped by maybe 200 meters and said, well, that's not realistic. Something must be going wrong there. So by bringing the skills he'd learnt in astronomy, by looking at very big data sets, he was able to look at this and say, there's something wrong here. We need to go and re-look at this bit of land and see what's going on there. Quite a number of people who've done PhDs or just degrees, they go to work in finance. So they go to work in banks and financial institutions. They're not sort of handling money or doing that. They're looking at models of how you might predict what's going to happen in stock markets or investments or things like that, and make up mathematical models for those. And of course, if you can work out how to work out what's going to happen with money, that is a skill lots of people would really like, because I guess in the end it will make you rich. So quite a few, I think at least 3 or 4 people I can think of have got on to work in finance industry, not sitting behind a bank thing, but in the back rooms working out how money moves around and how you can make the best of use of these things. Other people have gone on to work in things that are related to physics or astronomy. I know another colleague has gone on to work in one of the bureaus that looks at standardization. So, they look at how you make standards, how long is the meter, how long is a second. If you want to know exactly how long those sorts of things are, you have to come up with a standard that everybody can agree on. So I know somebody went to work on that. I know a couple of other people have gone to work in astronomy education. So now they've got a doctorate in astronomy. They've gone on to teach other people, but not at universities. They've gone to work in planetariums or in schools or in media. So I know somebody who works for the BBC doing astronomy bits and pieces for that. So that's another career. So you don't just have to be an astronomer, because there aren't that many astronomers in the world. I guess there are about maybe 5,000 to 10,000 astronomers in the world. So there's not a huge amount that you can become to be an astronomer. But even just going on the route to becoming an astronomer, you learn so many valuable skills that employers come to the university hoping to get people who've studied astronomy and physics to work for them. And it might be in a job related to that, or it might be in a job completely unrelated. But just having gone through that, learning the skills to be an astronomer makes you highly prized as a graduate compared to some other areas of doing a degree. So, I guess I'm a little biased because I'm very interested in astronomy, and I think it's a good thing to study. But even if you get bored with it, the skills you learnt will set you up for the rest of your life. So it's a very useful thing to study.
So Dr. Julian Onions, thank you for that. And one more thing that we have here, especially in Sri Lanka, is that most of the parents, they think that, astronomy should be taught in a physical classroom. But as for you, what do you think? Like, can astronomy be learned in, virtually, like how we do it here? Is that fine? Or is there any, does that mean that you have to be in a physical classroom? Is it necessary?
No, absolutely not. You can certainly learn it virtually. Even in the UK, where we have a lot of universities you can go to, a lot of people learn astronomy through remote teaching. So sometimes they have a little practical element, maybe using a telescope, but you can do that sort of over a course of a weekend or a week, and over several years that you study for astronomy. And some increasingly now, we don't even do that. So there's an institution in the UK called the Open University, which is all done by remote studying. And they have a telescope actually somewhere off the coast of Spain. And the students just connect to it over the internet and take the images they wish, and then get those images set back all automatically, so they don't even have to visit the telescope. That's all done remotely. So it is certainly one of the subjects that you really can learn by remote learning. It is certainly quite possible. There are some things that are probably not quite, if you want to learn medicine, it's really quite difficult to do that over this sort of technology, because you need to look at patients and study how they react and so on. You can do a certain amount, but there's nothing like having a patient there and working out what's wrong with them. But with astronomy, because it's all so distant anyway, you can certainly learn that, such as you're doing a great job teaching here at the Ceylon Institute.
Right. Thank you very much for that, Dr. Julian Onions. I hope the students understood that, because unfortunately they have a few issues with them. So they were thinking that, it should be taught in physical class, but thank you for your clarification. So I believe that they understood that this can be learned, virtually as well.
Absolutely.
So yeah, thank you very much. And also I just want to mention that this month in May, we do have the lunar observation by the German Space Observatory, which we will be witnessing virtually. So which is a really great opportunity. So we don't have to visit them. So we can, gain the same experience just by being at home. So which is really great.
Yeah.
So, yep. So thank you very much for that, Dr. Julian Onions. Thank you for your time. Thank you for joining again. I'm hoping to see you in the upcoming sessions as well.
That'd be great. Thank you very much.
Have a nice day, Dr. Julian.
Thank you all for coming, and thank you for listening to me talk. Best wishes for the rest of the day. Bye now.
Bye.
Bye.
Bye. Bye.